Hi, my name is Yanjing from USENIX. The title of our paper is Accelerating Encrypted Deduplication via SGX. This is a joint work with Jingwei Li, Zuoru Yang, Patrick Li, and Xiaosong Zhang. Outsourcing data management to cloud is common in practice. According to SGX statistics, about 22% of business data are stored in cloud repositories. The outsourcing storage should satisfy two goals, namely security and storage efficiency. For security, it needs to protect outsourced data against unauthorized access. For storage efficiency, it needs to reduce storage footprints to minimize maintenance costs. To meet both goals, we explore encrypted deduplication. It is a technique that encrypts plain text chunks followed by performing deduplication on ciphertext chunks so as to achieve both security and storage efficiency. However, traditional encryption is incompatible with cross-user deduplication because different users have different keys and encrypts identical plaintext chunks into different ciphertext chunks that cannot be deduplicated. Message-locked encryption is a cryptographic primitive for cross-user encrypted deduplication. The idea is to use a key derived from the content of each chunk to perform encryption, and the resulting ciphertext only depends on the content of the plaintext. This preserves deduplication capability on ciphertext chunks. One example of MLE is convergent encryption that uses the hash of each chunk as its key. In addition to MLE, the state-of-the-art encrypted deduplication builds on a server-aided architecture to prevent offline brute force attacks. Specifically, it deploys a key server that manages a global secret to generate chunk-based keys. It uses oblivious pseudorandom function, or OPRF for short, to prevent the key server from learning plaintext chunks. After encrypting each chunk, it removes duplicate ciphertext chunks via source-based or target-based deduplication. In the target-based deduplication, the client needs to upload all ciphertext chunks, and the cloud stores the chunks that have unique contents. In the source-based deduplication, the client first uploads the fingerprints of ciphertext chunks, and the cloud performs duplicate check by fingerprints and informs the client to only upload non-duplicated chunks. However, existing implementation faces two performance issues. First, the OPRF is known to incur high computational overhead and presents a performance bottleneck to the overall system. Second, the target-based deduplication incurs high bandwidth overhead for the uploads of both duplicate and non-duplicate ciphertext chunks, while the source-based deduplication incurs information leakage. That is, a malicious client can fake fingerprints to learn the deduplication patterns of corresponding chunks. To prevent this information leakage, source-based deduplication needs to be coupled with a cryptographic primitive, namely proof of ownership, but the POW is computationally expensive. Thus, we pose the question that how to accelerate encrypted deduplication while preserving security. In this work, we built on Intel SGX to speed up encrypted deduplication. We present SGX-Dedup, an SGX-based encrypted deduplication system with high performance. The key insight is to replace the expensive cryptographic protection in existing software-based encrypted deduplication implementation by hardware-based protection. We introduce three key designs in SGX-Dedup to preserve security and boost performance. We perform extensive experiments and show that SGX-Dedup achieves 131.9 times key generation and 8.2 times POW speedups over existing approaches. The overall prototype achieves 8.1 times throughput over the state-of-the-art encrypted deduplication system. We first introduced the basics of SGX. SGX has three security features. The first is isolation. It allows to allocate an isolated memory region called enclave to run sensitive code against the host system. In practice, the enclave is of limited size. The second feature is that SGX allows to verify the correctness of in-enclave content via remote attestation. Our experiment finds that the remote attestation takes huge latency in our region. The third feature is sealing. It allows an enclave to securely move in-enclave contents into unprotected memory via encryption, and ensures that only the same enclave can decrypt the saved contents for future access. SGX-Dedup is designed for two groups of goals. In the first group, it aims to preserve the goals of existing encrypted education in the protecting chunks and keys against unauthorized access while removing all duplicate chunks for storage efficiency. In the second group, SGX-Dedup aims to boost performance via a hardware-based approach. Specifically, it performs source-based deduplication to mitigate the transfer of duplicate chunks. Also, it mitigates the computational overhead of OPRF and POW. SGX-Dedup uses a server-aided architecture, but it deploys a key enclave in the key server to protect key generation, while a POW enclave in each client to protect source-based deduplication. The key enclave manages the global secret and is connected with each client via a secure channel for key generation. It performs key generation by hashing the concatenation of the chunk fingerprint and the global secret, and returns the resulting key via the secure channel. This mitigates the performance overhead of OPRF while preserving security, since the whole key generation process is oblivious to the key server. The POW enclave operates on ciphertext chunks and protects source-based deduplication. For each ciphertext chunk, it computes the fingerprint and generates the corresponding signature, which can be verified by the cloud. This ensures that a malicious client cannot fake fingerprints anymore, while mitigating the performance overhead of POW. However, realizing SGX-Dedup is non-trivial, and we identify three questions. First, how should the enclaves be securely and efficiently bootstrapped? The challenge is that the global secret needs to be securely bootstrapped into the key enclave, while we should minimize the bootstrap overhead of the POW enclave, since it needs to bootstrap multiple times with the client. Second, how should the secure channel be established? It is necessary to enable revocation on client's query key generation, since some clients may cancel the subscription of the cloud service. Third, how should the key enclave reduce its computational overhead of managing secure channels, especially as the number of clients increases? To address the first question, SGX-Dedup implements an enclave management approach. It computes the global secret from an in-enclave subsecret from the cloud and an input subsecret from the key server, so as to prevent either of them from learning the whole secret. For first bootstrap, it performs remote attestation offline. After attestation, both cloud and each POW enclave share a POW key to verify the authenticity of fingerprints. It uses sealing to avoid reattesting the POW enclave after its first bootstrap. Specifically, when the POW enclave terminates with the client, it sells the POW key into disk. When the POW enclave bootstraps again, it unseals the POW key and loads the recovered key into the enclave. To address the second question, SGX-Dedup shares a blinded key between clients and the key enclave for managing secure channels. It allows to revoke clients by updating the blinded key, such that the unauthorized clients no longer connect to the key enclave via the channel. Here, we implement the key update operation via key regression in order to support lazy update. After each key update, SGX-Dedup synchronizes the blinded keys between the key enclave and the authorized clients via the cloud. Specifically, the key enclave derives each new blinded key based on an in-enclave blinded secret, while the authorized clients download the up-to-date blinded keys from the cloud. To address the third question, SGX-Dedup implements an SGX-based speculative encryption. Speculative encryption builds on the countermode of symmetric encryption. For example, it encrypts each fingerprint by performing an XOR operation with a mask. It allows to compute the masks offline to reduce online overhead of the key enclave. The security requirement is that the mask cannot be reused. To implement the idea into SGXDedup, we assign each client with a unique nonce, such that the masks of different clients are distinct. Specifically, the key enclave manages a nonce index to store all existing nonces of clients. By default, the nonce index takes 3 MB to serve 112,000 of clients. In addition, the key enclave keeps a mask buffer to store the pre-computed masks for clients. Due to the limited space of enclave, we configure the mask buffer with up to 19 MB, such that it can be used to process the fingerprints of 11.25 GB data. We implemented SGXDedup in Linux with about 14,000 lines of C++ code. We use 2 real-world datasets to drive our evaluation. One dataset is FSL, which includes the backups of Linux user home directories. The other dataset is MS, which includes Windows file system snapshots. We do experiment in a local cluster with 10 gigabit Ethernet connection. Each machine is equipped with Intel Core i5-7400, a quad-core 3 GHz CPU, and 8 GB of RAM. We compare the overall performance of SGXDedup with Duplus and plain dedup. Here, Duplus is the state-of-the-art encrypted deduplication system, and plain dedup is a plain deduplication system without any security protection. We upload the same 2 GB file for 2 times, and then download the file. The left figure compares the performance of 2 uploads, where we use a networking tool to control the network bandwidth of our experiment environment. The x-axis is the controlled network bandwidth, while the y-axis shows the upload speed. We see that the performance of Duplus is always bounded by the OPRF-based key generation, while SGXDedup achieves 8.1 times and 9.6 times speedups over Duplus in the first and second uploads. Also, the second upload of SGXDedup is faster than the first upload since it uses source-based deduplication and does not need to transfer data again. The right figure compares the download performance. We do not present the result of Duplus since its download mechanism is identical with SGXDedup. We see that SGXDedup incurs 44.2% performance drop from plain dedup due to the security mechanism. Our paper provides more results for SGXDedup. For example, the aggregate upload speed for 10 clients can reach 637 MB per second, and it achieves 9.7 times speedup over Duplus in real cloud deployment. We replay our datasets to compare the trace-driven performance of SGXDedup with that of plain dedup. We upload each replayed snapshot in order, followed by downloading each of them in the same order. In each figure, the x-axis shows the order of each snapshot, while the y-axis shows the upload and download speed of the corresponding snapshot. We see that SGXDedup incurs 21.4% upload performance drop from plain dedup since we now disable chunking to replay each snapshot. The bottleneck of SGXDedup is POW, while that of plain dedup is fingerprinting. The download speed of both systems is similar since it is bounded by chunk fragmentation. In conclusion, we present SGXDedup to mitigate the performance overhead of encrypted deduplication. The idea is to offload expensive cryptography by directly running sensitive operations in enclaves. The source code of SGXDedup is published and can be accessed via the link below. Thanks for listening.